presentation. We're group STeam12, and our project is the ASME Student Design Competition Remote Inspection Device. A little bit about the problem statement that has to do with our competition. It's based on the tsunami and earthquake that hit the Japan nuclear facility in March of 2011. The nuclear industry issued a request of proposal to build a proof of concept robot that would enter the facility, inspect for any damages, determine the level of radioactivity, and protect the human operator from any radiation. So some of the tasks to be accomplished during the competition is to navigate the course while avoiding obstacles, to pick up and drop off a radiation sensor, to push a button to initiate the cooling cone, and to obtain a pressure reading. Return to the initial parking area, all within 5 minutes, and the operator will not be able to have prior knowledge of the course, and will only be able to use the cameras on the robot to view the course. Now I'm going to pass it on to Sebastian, who's going to talk about our design.
Okay, so we went through several design changes. I'm going to speak about the different ones and some of the main characteristics that were involved in it, some of the problems we encountered, and what we did to overcome it. So the first design is what we originally had. That design has the caterpillar tracks. We learned that the surface of the competition was not going to be rough terrain, so that was that design is not efficient. We need 4 motors, and also too much friction is generated when you're doing the skid steering. So we changed it to a drive system, 2-wheel drive in the back, and we put 2 wheel casters in the front. And this design worked, but the camera when we tested it, the camera ended up being a little too heavy for the robot arm. So we had to bring the camera down to the chassis. We had to make some modifications to the chassis, add a couple of servos to the chassis, and create a pan and tilt system. And we thought we were done, but then when we were testing, the wheel casters, when you were driving, they became very unpredictable. So let's say if you had just made a right-hand turn and you went to go straight, the time that it took for the wheels to center and go the direction you wanted to go, it would kind of shoot your robot off in one way or another. So we would always have to be adjusting it. And then that brings us to the design we have now, which we named the Inspector. And the material that we used to create the chassis is HDPE, high density polyethylene, and basically a cutting board. We went ahead and the wheel casters were replaced by a single ball caster in the front. And this caster it has no input on the steering, and the ball is big enough so that it could travel over any kind of small obstacle, or it doesn't get stuck in small obstacles. So here's a little bit of details on the pan and tilt system that we built. Like I said, we have to put the camera, the case, we have to put it on a servo to do the panning, which is what you see on the left-hand side there. And then we put a servo on the back of the case attached to a wire that is connected to the base of the camera. So when the horn goes up and down, you're able to, that creates the tilt system on it. Here's the details of the bottom of the robot. And as you see on the left-hand side, that black wire that runs there, we put all the components in the bottom, or some of the components in the bottom, not just for space, but to isolate noise. We have some noise with the electronics, so that's the video wire that runs down there, and we noticed that helped quite a bit with the noise coming from the system. Here on the left-hand side is the motor controller, and the way that works is the microcontroller that we use, which we use in Arduino. It sends signals to the motor controller, and the motor controller reverses the polarity of the voltage that allows the DC motors on the left-hand side there to either go forward and backward. And the motor, as you see, it's relatively small, which ended up being kind of one of our downfalls, but I'm going to get into that a little bit later. We decided for global learning, originally we were going to use Wi-Fi, but in order to incorporate the global learning aspect of this project, we decided to use radio frequency. So we were able, so this thing can be taken anywhere, and as long as you have, and it has rechargeable batteries on everything. So it can be taken anywhere and set up and run. So and that ended up being one of our saving graces, where if we would have used Wi-Fi, a lot of the teams which did, they didn't really even get to compete that much because there was basically no Wi-Fi there. So that was really good for us. Here you see that's the XB radio frequency module. what that does is it receives commands from the Arduino, and it sends it from the computer, and it sends it to the Arduino, which controls all the motors and everything. And then there you have your video transmitter on the left-hand side. And this is our video receiver. And what it is it's a repurposed. It was a beer cooler, but we gutted it all out, and we put in the video receiver. We put in the battery. We put in the video converter. And a switch to a nice, neat little package, so it's easily transportable. And at the back of it, what's piggybacked on the back is all the switches for each of the batteries that's on the robot. We decided to power each major component with its own separate battery. And then we also have the emergency stop button, which is required per the ASME competition. And now Ryan is going to speak about the robot arm.
Right. Good afternoon. I'm here to discuss the design and assembly of the robot arm that we did for this project. On the right side of the screen, you see right now is the modified gripper that we attached for this project. It's actually a kit already assembled and readily available from Robot Shop. On the tips of the gripper that we have, you see the polycarbonate material. We added that to have a bigger grasp of the material that we're going to be holding, and added some anti-slip material, to hold the material much firmer. On the right side of the screen, you see is the brackets that we use for this project. Again, we use aluminum materials and polycarbonate material for this project. We use this kind of materials in order for it to be as much as possible light and mobile as possible. We added some fasteners in order to secure those brackets that we have for the robot arm. The robot arm that we have for this project actually consists of 5 servo motors. Each joint has attached a servo motor on it, and the base of the robot arm that we have for this project also is a kit. It's readily available. We have to assemble it and incorporate it to the robot arm that we have for this project. For the motor selection of our robot arm, we have to do this correctly in order for us to determine the required weight for the motor to support the robot arm on it. And then also another factor for this to be able to determine is the arm length of the robot arm and the weight it has to carry. Another principle for this R project is keep the heavy components as much as possible close to the base. As Sebastian mentioned earlier in our initial design, we had the camera attached to the robot arm itself, but it proves to be hard or difficult actually for the robot arm to move as much as quicker as it could, because it added too much weight on the robot arm. So we had to change our design and have the camera attached to the base of the vehicle, as you can see in our final design on it. And another thing, we added some springs, because during our testing, we have the robot arm sagging and trying to center itself. So we added some springs to reduce the torque applied to the motors itself. And here is Maribel to discuss the programming part of this project.
Okay, so here's the basic layout of the keyboard for all the commands that we made for our robot. The basic ones are the camera controls, the drive controls, the 3 joints of the arm to control the base and to open and close the claw. But since time was such a crucial component in this competition, then we decided to make some preset positions to save time. The first one is pickup position. So it drops the arm down from wherever it's at, drops it down close to the ground and opens the claw. So we just need to do minor adjustments, and then we can just close the claw and it's picked up. Then it goes to the travel command, travel position, that retracts it but keeps the object in view of the camera just a little, just so we know if in case it falls or it tips something, anything that happens, we know immediately that it fell, that the sensor fell, that we need to pick it up or something. Then the drop position, it again brings it down to the ground close, because given if this was a real situation, these sensors are very delicate and you don't want to break and drop them from a high distance. So you bring it close to the ground, and then when you're ready to drop it, you just open the claw and fall. And then when you're not using the robot arm at all, there's a home position that retracts it completely, keeps it out of view and centered. And then a little bit about our finances. Our original budget was $1,000, but due to some replacement parts and motors that we had to rebuy and that weren't enough torque, we had a lot of replacement parts, and our expenses to Alabama were also more than we expected, so we exceeded this budget. And now I'm going to pass it on to Sebastian, who's going to talk about competition.
Here's a video of the actual competition. We start off in the parking area, which is taped off, and as you see, the robot starts with the actual sensor that was being used. Now, just to mention again, some of the objectives we have to do is we have to pick up the sensor, we have to drop off the sensor at a given location, we have to press a button, read a gauge, pick up another sensor, and come back to the parking area, all under 5 minutes. What you see here is we're right now. The issue was the left hand side is all the operator saw. It was nowhere near as clear. There's a lot of static. It was hard to tell where you were. The first objective that we approached is the drop-off sensor location, and what you're going to see now is one of the preset functions which brings the claw close to the ground, and then the operator just manages it and drops off the sensor, and then as they wish. And we're going to approach the next objective, which was to pick up the sensor. And this is where the camera we used is very wide angle. It's 170 degrees, and it worked very well for navigation to kind of get your orientation of where you were. But as far as it kind of killed a little bit of the depth perception that you had. So right now, keep in mind this video is about 2.5 times faster than what actual was. So we spent a good amount of time trying to reach the sensor due to the depth perception and stuff like that. So, but once we got the sensor, we went ahead and we continued navigating. The 2 straws that you see, when we were testing, we realized that we had no idea how wide the robot was because the camera is very up front. We couldn't see the chassis. So we kind of had to improvise, and we put neon straws at the end of it so we can have an idea of how wide we could fit into things. What you see, that's the gauge we had to read to the judge that was sitting next to the operator. The judge wouldn't tell you whether the gauge was right or wrong. You just have to give him the number, and you know, if you had to have a good video system to be able to read the number properly. And you're about to see is the button being pushed to activate the cooling pump, specifically the cooling pump. Now, the first time around, when I came around, because the camera is very low and the video feed was a little blurry, you're going to see that red line that's along the wall there. I actually thought that was the edge of the competition. I thought that was one of the boundaries, so I didn't go over there. So, you know, we wasted about a minute, I would assume about a minute, traveling back and getting lost in that sense. So we definitely could have improved our time quite a bit more. Here, again, video lag, so I was overcompensating when we were turning back to home base. The competition ended up being, we were about 7 seconds before time limit. So all that, you just saw 5 minutes. Competition overview. In total, 30 teams competed. Some universities brought multiple robots. The University of North Carolina, which was sitting next to us, they had 18 people working on their one robot. Virginia Tech had 16. And 3 of us, we ended up being in 9th place out of all 30 teams. It was said to be one of the toughest competitions there. If you look at videos from other districts, you see some of the, you know, it was the course was very minimal. 2x4s. That's pretty much all they set up. Nobody was expecting to have water bottles, towels, tape. Nobody was expecting to have that kind of setup. So a lot of teams got hung up on that, but we managed to do pretty well. Some of the things we learned from this project. Definitely, we could have did a much better job if we had faster motors. But by the time we got to the testing stage, and remember this competition was held April 6th, so our timeline to finish this was much shorter than that. So by the time we started testing and everything, it was kind of already too late. We had the motors incorporated, so we had to sacrifice some speed in order to get better torque. Again, like we mentioned, if the camera placed on a higher surface would have allowed us to, on an actual robot arm, would have allowed us to have a better view of the course. We wouldn't have gotten confused and seen mistook a red line for a blue line. And some better shielding for the video system. That's definitely a must. And wouldn't recommend anybody driving 13 hours to Alabama in one shot. Before I wrap it all up, we put a lot of hours, we put a lot of time, a lot of energy into this project to try to make the competition. And but none of it would have been possible without Southern Gear helping out. They funded most of this project. We were able to get some extremely good components and make 9th place in the competition. Also, Melissa, she was amazing, wealth of knowledge. You know, without her, we would have broken many more items, so this project would have been way more expensive. And that wraps up our presentation.
Very good. Any questions?
Well, let me start. First of all, congratulations on coming in 9th out of 18. That's very good. Now, in your report, you said that you're inexperienced in building robots and also in working with circuits. Why didn't you get an electrical engineer or to be part of your team or for the very least have one as a consultant?
Honestly, I thought it was going to be easier than it really was for circuitry part of it. But it ended up being not.
Melissa is an electrical engineer. She's doing her graduates now in mechanical, but we were sort of relying on her a little for the electrical components too, but we kind of did a little too much on our own before we realized that we should have gone to ask for help earlier.
Yes, sir.
It's like an incredibly fun project and a lot of work. I admire all your work. Quick question is, why did you go with one camera or one without an adjustable telephoto system?
Well, that would have required us to have a different video converter. This camera is very good with angle, you know, and we thought it was going to work. You know, if we needed to look at different directions or something like that, this camera would have worked. But like I said, the video converter, by the time we purchased it and then we started realizing these little flaws, you know, it's kind of the deadline started approaching very quickly. But a lot of teams didn't have that. A lot of teams had a camera at their flaw, and then because they've probably seen other videos of where the course, everybody was expecting the course to have just little 2x4s, you know, but these walls were about 2 feet high. So you saw a lot of teams that had their camera higher up to try to get that extra advantage, but it didn't work.
Actually, the initial design we have for this project, we have 2 cameras, one attached to the side and one in the front. But it proves to me too much clutter on the electric circuit side of the project, and also it might try to interfere with each other, the video reception and stuff like that. So we decided to just go with one camera.
Susan, did you have a question?
No, I was wondering if you had had any idea of what the layout, not so much the height of things like that, but the layout of what the course would look like, or had a previous course layout that you could have put up and then tested to see whether or not your camera would have done that.
Each one of the districts was different, but no, we had no idea. We just knew how big things were, you know, the length that we had to travel, and basic information like the operator wasn't allowed to see the course prior. We were actually taken to a room, our cell phones were taken, and each driver had to be totally isolated from the team throughout the whole competition.
Actually, there's some videos posted on YouTube, the previous competitions from other districts. As you can see, as Sebastian mentioned earlier, it's like 2x4, it's like really basic course. And that's basically what we do on it, just like a couple of boards on the floor on it. We just run through it and basically simulate all the tasks that they require on the competition. But as Sebastian mentioned again earlier, we were not expecting that difficult course on the actual competition itself, with the debris everywhere on it, with bottles, rags, duct tape actually, which proves to be much more difficult, especially those, as mentioned earlier, the lines, extra lines on the basketball court, which confuses the operator itself, which are rather difficult. So,
anybody want to see it work?
Sure. You want to demonstrate? You got a couple of minutes.
I'll make a comment while he brought this to the company, and we got the whole company together down by our shipping department. He ran it all over the place.
Oh, by the way, I didn't point that out. The company that sponsors this project, that's the main man right there.
Yes.
That front wheel is brilliant.
Thank you.
The simplicity of it is brilliant.
So this is, I'm going to take it home. This is out of the way, out of the viewway. So let's say if we had just found the sensor, then that's the, I just found the sensor location. And then once you pick up the sensor, just close the jaws, and then you've got the travel position, and then you have the drop-off location. and then from there you would open the claw, and then you can bring it home whenever you want. The camera also has we got one of the gear motors locked up a little bit, so it can't really work that way. But here's the panning. There's a tilt system there, and then you have also functionality of the base. The base rotates. So we got a lot of modularity with this. Got a lot of thumbs up from a lot of people. And that's it.
Well, thank you, team number 12. No more questions, so we appreciate your presentation.
Thank you.
We're going to wrap this program up. Going to invite Caesar up to say a few closing remarks and take care of